Hey everyone, 2.3 techniques for computing limits. We're going to take and basically evaluate a bunch of limits today. I'm going to start with a couple polynomial functions, and evaluating polynomials is nice because polynomials are continuous on their domains, which are all real numbers, so we don't have to worry about holes or asymptotes or anything like that. When we get to rational functions, that's when we got to do a little bit more with it. But so for these first four, if we're going to evaluate these limits, basically what we're going to go ahead and we're going to do for this first one is we're going to input 4 for x. So we're going to take f of 4, and we're going to see what that y value, that output would be. If I do that, an input of 4, I'd end up getting 3 minus 6, which is negative 3. So this limit, as x approaches 4 of f of x, would equal negative 3. Likewise for the next one, this would just require us to use an input of negative 2. And when we input a negative 2, we get a negative 3 halves minus 6, which I believe comes out to be negative 15 halves. So again, the limit as x goes to negative 2. This is a two-sided limit. Right? We're not testing one side at a time. We're just testing and evaluating this limit. We get negative 15 halves. G of negative 1. If we take the limit of g of x as x approaches negative 1, we would get negative 2 minus 4 minus 1 plus 6, which gives us a negative 1. So the limit as x approaches negative 1 of g of x would equal negative 1 as well. And then finally, our limit as x approaches 2 of f of x would be the same as f of 2. And we get 3 halves minus 6, which gives us negative 9 halves. So the limit as x approaches 2 of f of x equals negative 9 halves. So with polynomials to evaluate, we just do a direct substitution. Like I said earlier, like for linear and polynomial functions, direct substitution is used, and we will always try that first. That'll kind of be our first screening process. So for this example, if I want to know the limit as h approaches 0, I plug in a 0 for h, and I would get the following. I'd get 3 over the square root of 16 plus 0 plus 4. So the limit as h approaches 0, not infinity, 0, of all of this, right, would equal, looks like 3/8. So when evaluating limits, your strategy should always be direct substitution first. Theorem 2.4, limits of polynomials and rational functions. Polynomials are, they're very easy. We just plug in. So the limit as x approaches a of p of x will just be the output for p of a. With rational functions, it gets a little bit interesting. We can still use the same property and plug in p of a and q of a, provided that q of a does not equal 0, and that's where holes or asymptotes might show up, and that could alter our limit output, or that value for our limit. Okay, so when using direct substitution for evaluating these, there's 4 possible scenarios. So first scenario, which we like the best, is we could get an actual value, right, like we did on the last page. So I'd just take this function and plug in negative 2. I would get 4 plus 4 over negative 2 minus 2. So it looks like I'd get 8 over negative 4. So it looks like this limit would equal negative 2. Okay, that's pleasing, that's done, we are finished at that point. If we get 0 over a number, like this one for example, I plug in a 2, I get 6 minus 6 over 2 squared, which is 4, that's 0 over 4. technically we're getting a similar answer to what we did before, except now it's 0. So we get a limit, and that limit exists, and it is 0. So we do direct substitution. If we get a number, great, we're satisfied with that. If we get a number over 0, right, like this one here, if I plug in a 0, I get 0 minus 8, that's negative 8. And I get 0 cubed minus 3 times 0, which is 0. If you get a number over 0, this answer does not exist, right? You could also say, you could argue, well, this would be equal to negative infinity, right? Basically, it doesn't exist. So we could go with either this notation here or DNE. Okay, now this is where a little bit more work will be required of us, and we're going to learn a little bit more on this on the next lesson. But if we get 0 over 0, example here, if I plug in 3 for x, I get 9 minus 9 over 3 minus 3. That gives me 0 over 0. That tells me there's more work to be done. So I kind of leave it hanging there and say, there's more to be done, more work required. And it might end up being, an infinite limit where it doesn't exist, or it might have a numerical value. So it's got possibility to be one or the other. As you'll see here with scenario 4, we'll need more information about the graph, and you'll see that using this Intro to Limits worksheet, as well as the graphing calculator. So that's 2.3, day number 1 in the books.